Hey everybody, this is my dad and I. Hey, say hello, Dad.
Hello, Dad.
We are here because he and I wanted to do this for a long time. One of the things we realize is that something like the particle model to be actually adopted by science isn't going to happen probably during our lifetimes or even our children's lifetimes. Who knows? As my uncle Dick said, perhaps hundreds of years. So we're going to be talking as if it were adopted, talking to the future generations. And this is either going to be historic or hysteric and lost forever. But regardless, if you're interested in the particle model and what my dad came up with in the last 5 or 6 years, it's an incredibly interesting model. Then this is the chats for you. You can join in. If I do see you there, say hello in the comments. Or if you really want to join us live, you can do that if you go to live.universehack.org. Do I have that one? Probably not. So I need to put that up there. Um, here's the one I need to edit here. So we'll just do live.universehack.org. And if you want to come in and say hello anytime, we're broadcasting to our YouTube channel for the book, Principia Mathematica 2. We're broadcasting to our Facebook page as well, and to my personal Facebook page. So if you are interested, then of course you can join us live by going to live.universehack.org, and you can say hello to us. But regardless, today we're going to be talking about our model. And Farouk, how you doing, Farouk?
Hey,
Hey.
nice to see your name up there.
Yeah, I know. It's he's from Morocco. I actually went to Morocco. I went to Tetuan, Morocco. And I won't tell you what year. I think 1986 or something like that. Maybe probably before Farouk was born. Hey, Mohammed, glad to see you. Hello.
Oh,
Hey. So we're gonna play a little video here, just warm things up, and we'll be talking. Again, we're gonna be talking about what if the particle model is actually adopted by the science community. So, hello, future, 150, 200 years into the future, maybe that would happen. Here we go. So this is our book. You can get an autographed copy of the book if you go to our website, principiamathematica2.org. And that's how you can get a copy. If you go to universehack.org, you're going to go directly to Amazon. So we do have the paperback, and we have them here. So if you guys are interested in our book, you can send us an email. Oh, no, you go to the website, principiamathematica2.org, and there you will see how you can click and see how you can order one online. We'll write something in the book for you and send it to you so you can save it for your future generations, so that it'll become very valuable in the future, or it will become a doorstop today. So anyways, I just thought it would be really wonderful for my dad and I, because we've kind of gotten away from the book. Actually, after 7 years working on the book, we got burned out on really working on it, but it never stops because we're always talking about it. So I mean, what I was thinking, Dad, that one of the things is this: people think that a theory that you're going to have, or a model of the universe that you're going to have, that's going to would be accepted by science, would be some set of equations, right?
that,
Seriously, right? It's
yeah,
equations.
that would Yes, math is dominating the
Right.
science world. Yes, absolutely.
And there are a lot of people who talk about their own theories, which is great. There's a lot of great models out there, Jeff Eade, Glenn Borkert, other people, and they all say this is very easy to understand. But then when you start looking at the math, it gets to be tough. But I think in our case, oh, can we increase the sound, please? Okay, let's see. We can do that. Gain. All right. Is this better, Farouk? Let me know if the sound's better. Yes, no, maybe. Um, I'll check the sound volume here. So, okay. Anyways, let me know, Farouk, if that's better for you guys. Because that's one thing people don't like is the, not really? Okay. All right, so let me go to the sound settings and see here for the input mic. Oh, how's this? This must be better. Oh my gosh, I got the
Why
wrong
are
mic.
you yelling?
Is the mic? Is this better now, Farouk? Hopefully.
That was before.
Let's see. Audio. Oh, there we go. No, it's there. Oh my gosh, I didn't set that. Right. Oh, that's not speaker. Speaker's this. Yeti. Okay, 1, 2, 3. 1, 2, 3. Yeti, Yeti, Yeti. Yeti, Yeti. 1, 2, 3.
Okay.
How about that? Is that better now? Okay. Boy, and so I'm talking to you guys. I'm sorry about that, folks. So I think we're better now. Let me know. I know it takes a little while for us to go there. But again, what we're talking about, just Farouk, if you can let me know if that in fact fixed the problem. But we are very good. All right. Okay. So we're good. I had the wrong microphone. See this microphone? This is a nice microphone. I should have selected that because we hadn't done this in a while for our channel. So the idea is really simple, is what if, this was accepted? And like I said in the beginning, my uncle Dick, your brother-in-law, actually read the book and wrote it, and he said it was very, very intriguing. But he said it's going to be maybe 100 years before people are going to be used to it.
It's a big shift.
Yeah, it is a big shift. And I was thinking about what the big shift is, and the big shift really, really is that it is a different type of model. It's really it's taking Borkert's neo-mechanics. What is neo-mechanics? You know how people say about the universe, because I'm going to talk to people who aren't, necessarily really into the science as much as a lot of us are. But when you look at science itself, you see a lot of equations. You see a lot of talk that's kind of hard to understand. You see models with, atoms and quarks and Higgs bosons and all this stuff, and we have four forces of the universe, which are the strong force of the inside the atom. You have gravity.
There's only two.
There's only one, and then and so there are new models out there like ours. We're not the only one. There are a number of them that treat all the forces in the universe as hits of mass on mass. Something hits something, and that's how all forces that way. So when we think of a magnetic field and there's a force there and you feel these magnets pull together and it's really strong, well, we say there are they're particles, they're real things, physical things that make magnetism, that make gravity, that make electricity, make light. And the difference, I think, is we talk about the entire universe as mass and motion, which is neo-mechanics, which is Dr. Glenn Borkert. But we say that the entire universe is made up of how particles move. That there are particles infinitely up, that particles get bigger and bigger and bigger, so that we have the Earth goes around the sun, that's a solar system, the sun's part of the galaxy is part of a supercluster of galaxies, and those are bigger and bigger and bigger structures, and that you have atoms have a nucleus and things that go around them, and those have pieces, and those have pieces, and those have pieces, forever and ever. It's called the infinite universe theory, which is, again, Dr. Glenn Borkert's theory, and so that's what we're looking at our model. So our model comes down to what we have our t-shirt. We do have t-shirts if you're interested, and it's on the cover of our book. Thank you so much. Who was it? It was Luis Sauerbaum from Brazil. He's an engineering professor at the university in Niterói, Brazil, on the other side of Rio de Janeiro. And he said, put this diagram on the book because it tells everything. So that's really what the model is. The universe is just moving mass, all of it. There's no magical force. You can't have light or magnetism or electricity without really having something real. And that our model is not a model of mathematics, but a model of particle movement. And so when particles move in a circle, they can cause magnetic fields at all the levels. You know, someone asks you, here's a question for you, Dad. Is the moon going around the Earth a magnetic field? According to our model?
According to your model, because it's in orbit, it's in orbit, it's circular motion.
Right. And so we say that when you look at the underwater experiments from, Deneuve, where he spins things, you can see very clearly that spinning particles cause magnetic fields. So we can classify everything. If things move in a straight line, if particles move in straight lines, then we call that electricity. If particles move in waves, like bombers, you can see that here. That's my dad's solution to the wave-particle duality right here. If you see that, like right here, then those are light waves. And if you see particles going in random directions, it's a gravitational field. So that's it. And of course, can you hack the universe? And that's what we spent. That's why we say universehack.org. We have that domain name there. If you can see, it's hacking the universe with these four movements. And we have, for instance, in the atom, you have particles going around the nucleus, and for particles to go around the nucleus, you have a little gravitational field at a different level. It's not the same gravity, but it's different, and you have a smaller particle making the gravitational field. And at that level, we have magnetic movements even inside the nucleus and inside of an atom. And that is something, Dad was looking. I said, Dad, didn't you know we did that? And he goes, no. So basically, we have that here. I'll show you a picture. Here it is.
Reread the book.
Here. So this is like Jeff Yee's work. There's the Yee structure of the atom, and you can see there that you have protons or quarks. What do you want to call them? We're not saying really all those kinds of things. We're not making any new claims about anything. But you have the G1 particles going around. That is what they call electrons, what people call electrons. And for it to go in a curve around something, it's got to have its own gravitational field. So down a level, you have even a smaller. So the gravity that we're used to is G1 particles. The gravity that is needed for electrons to go around the nucleus is a G3 field, which means it's smaller and small. It's smaller particles down there. So you have G2 field, and there are magnetic fields. And Jeff Yee has actually modeled this, and even though he gives it equations, we say that what we observe, the reason you have the way the electrons go around an atom, they don't just go around like a circular orbit. They're moving around in kind of different orbit, SPDF orbitals. So just imagine you have a nucleus and they're going all around. Well, those G1 particles, if it goes around, there has to be a force field that makes it go around. And in our system, the simplest field is the gravitational field, like you see here, right there. And that gravity field is just particles going in all directions. In fact, if you think about it, what's the most basic field in the universe? It's particles out there going in all different directions. It's kind of like what you would imagine, oxygen is, and
we're breathing in the air. It's particles going all around. Yeah, we have gravity kind of push them down, but that's the idea. So the whole idea of the particle model is that we classify all movement of mass in the universe as 4 different kinds of movements. And I think that it's just not the way people come up with models, right? People don't come up with models that way. I mean, they always have some magic in them, right? That's why you see in our book all over the place, the universe is not magic. Look at the top, the universe is not magic. And they always end up with something.
Well, the terminology is sort of abstract, and you don't get anything to grab onto. But in our case, we start with the particles and the atoms and molecules, and so we're talking about something real, and I think that helps make it understandable.
Yeah. I think, I mean, when you see everybody else, even Electric Universe, and again, I think the Electric Universe people are great. Anybody who says, we have to look at science and redo it, you got to support them. You don't have to agree with what they say. I mean, the universe has a lot of electrical things. A lot of things that people in the Electric Universe predict actually happen. The thing is that they say it's all electric and that gravitational is part electric, but they don't. When you ask them what electric is, they tell you electrons or electric fields. What are those? Magnetic fields?
I am doing a current experiment. I've dropped it for a little while. I'm doing a current experiment with circuits that will actually show that the function of the electron going around this circuit is mechanical. It shows how that when the electron goes through a resistor, and when it hits, it gets lost.
Yeah, you think about it, folks. Let's say you don't have to understand anything about an electrical circuit, right? Everyone knows you have to have a battery or you have to have electricity going through the circuit, right? Everybody knows that. And so we know there's electricity. It's a force. Put your finger in the wall and go see if you want to see that it's not a real force. It is a force. It causes people to be pushed back. It causes all kinds of things. People to be fried. And it's manipulated. Basically, electronic circuits just manipulate it. And to think about a resistor, you have electrons. We call it a G1 particle. It's a particle. It's going through the atoms of a wire, right? It's passing through all the nucleus is kind of the way we say it is guiding. Imagine you have all these suns lined up in the universe, and if I threw a comet through it, that gravitational field would be like you can make the gravitational field that it stays, going through. So it's going through it, and it gets to it as a resistor, and what happens? It hits something and is ejected. That means it literally goes out of the circuit into the world.
And that tells you that as you go around the circuit, the current gets less. Going from the negative battery around to the positive through the circuit. Every time you lose some, the current is dropping. It's a very small amount. And my experiment is going to measure that using a 7.5-digit multimeter.
Yeah. So what he's saying is that in electrical engineering, current, which is the flow of electricity, right? That's what they say. A current around a circuit, oddly, and it does make sense. Actually, it's kind of counterintuitive. I mean, electrical engineers, if you measure the voltage around it, is it the voltage that they're measuring, that the current? Or?
Well, if you're measuring current, there's ammeters to measure current and the voltage. I'm measuring voltage primarily, along with some 1 milliohm sense resistors, to be able to determine this small change that's going around. Kirchhoff says no, the current's the same all the way around the loop. I'm saying, Kirchhoff, sorry, but if you look close, you're wrong, because you lose these G1s as you go around. Therefore, the current drops infinitesimally as it goes from one resistor through another. That's what I'm trying to show with the experiment and measurements I'm making.
So basically, what he's saying is that particle model makes a prediction about electronic circuits, a very simple one, and that
it's
goes
mechanical.
against. Yeah, it's mechanical because our whole model is mechanical, but it goes against what my dad's an electrical engineer. What electrical engineers are taught is there shouldn't be any loss of current around a circuit, but he says yes, our model says yes, and we have a voltmeter that's like over $2,000 that can go out to 7 decimal places, and at that level you should see then the current's going to be different. So, but let's go back to the particle model and accepting by the the whole. I mean, if people are watching this into the future and this actually gets adopted, I mean, I guess where do we have to get to a point where people are going to kind of look at this? What's going to be, I don't know what that is. I don't know what it's going to take. Glenn Borkert says that you have to have these revolutions in science and society where everything gets upended so people kind of look. But I think part of the reason that I was so interested in writing this, well, no, it's probably the number one reason, is I got tired of all these things we talk about, light and gravity and magnetic fields, especially magnetic fields, even electricity, all these things, and no one telling you what it is physically, right?
Yeah.
I mean, even everybody's models, they have some kind of magic going on. Even Jeff Yee's model, which I think is one of the best models out there, he still has a magnetic field, or he has some type of field, or he has some force where he puts an equation in. He says too that everything's mechanical. It's all Newtonian, that there's all these weird things like, quantum forces and, all these things. But I just got tired. Just tell me what gravity really is. Don't say it's space-time and some equation for that. I mean, it doesn't make sense to me. So that's the reason I'm so interested in this model, is because it gives physicality to everything. Right or wrong, it gives physicality to everything. I mean, it's just, what do you think about that? I mean, it's giving, I know that Ian in our group says physicality doesn't matter. I think it's just really hard. I guess it's just a utilitarian idea that it doesn't matter, because if you can predict everything, we don't care what the model is. But I mean, isn't there some kind of innate, aren't you curious about the universe when we see all these things, what it really is, magnetism really is?
Well, I mean, obviously, any scientist who tries to understand it, yeah, we're curious about what it is physically. And as you point out, you can have models that attempt to describe it. Some of them are mathematical. Some of them may attempt a physical model like we have. But I think what's really interesting about the physical model that we have is that with the G1 particle, in particular, satisfying all 4 of those functions of gravity, magnetism, light, and electricity, one particle doing all of that is something I don't think anybody else is saying.
Well, yeah, but that comes from this. Why would we propose the electron, the photon, the magneton, or the graviton? I guess the magneton I just made up. But why would we propose that it's all the same particle? Because they all travel at the speed of light. In fact, this gravity speed travels at the speed of light. Mainstream says gravity travels at the speed of light. Also, we know that actually light travels at the speed of light. Magnetism travels at the speed of light. If you want to know how you can, in your mind, without just kind of a thought about how that would work, is we know that particle accelerators, right? We accelerate particles using magnetic fields, and we get them go faster than the speed of light? Nope. It's always approaching the speed of light. So if that's the case, what we look at is that's a mechanical model. Something's pushing that particle, and what's pushing it is a particle that only goes as fast as, at the most fast as the speed of light. So if you have magnetic fields pushing particles, and the mainstream science says, nope, they don't go faster than the speed of light, then magnetism, if it is a moving mass, can only go at the speed of light. So you have an electricity course, even though we all know that electricity supposedly goes at the speed of light. So that's why we claim that, if gravity goes at the speed of light, it does magnetism pushes things close to the speed of light, but not faster. Light, of course, goes at the speed of light. And electricity, we know, moves faster at the speed of light, then it's the same particles. So the same particle is responsible for gravity, responsible for magnetism, responsible for electricity and light. So how are they differentiated? What makes, if it's the same particle, you can't say that's light. Here's a particle. Is it light? No. It's not a particle, right, that makes it light.
No.
It's not a particle that makes electricity. What makes it what we call light are waves of them. If we have waves of asteroids that come at us at a frequency like every month, there's waves of asteroids coming at us, that gives us a frequency and a power because of how many of them are. If I'm an astronomer at that time, I would start thinking, what's sending these and why is it this frequency? It's information, right? That's one of the things I told you
I know.
when you came up with that's why we're even here. It's because of Dad's model for light being waves of bombers, waves of asteroids coming at you. I told him, I said, what makes that interesting? It's information. Light bounces off all this stuff. You're watching us now with light.
Farouk has a question.
Yeah, I do. I will put that up there because if I put it up there, it's going to change the subject right now.
Yes,
so, Farouk, I'll get to your question, absolutely. So you have all these waves. So waves transmits information. So it's not the particle itself. Any particle, the Earth, can be part of a light wave. Our galaxy could be part of waves of galaxies. If our galaxies end up going in random directions, our galaxies create a gravitonic field. If just like we have gravity here that's pushing us down. So that's the kind of thing that we're talking about. So it's not a particle. You don't have a photon. You don't have an electron. You don't have a graviton. You don't have a magneton, because those one particle by itself is nothing, right? You can't build a universe with one particle. It's hard. It's so funny because it takes two, yes. A male particle and female particle. So, that's why we do have those, a little circle with and it's even got a vector on one of them. So, anyways, it's, boy, that's weird. But what I was saying, universe, the idea that some people think that the universe could be made of one particle. That's one of the ideas, right? You start with the atom, and atoms, there's like 4 of them or 3 of them. Or then you get down, there's lots of atoms, but no, there's electrons and protons and neutrons. And so there are 3 particles. And then the idea is, let's make a quark and then be able to describe everything as a quark. Of course, you got 6 quarks, but the idea is that people were kind of, where in the universe, let's get it to one particle, and the entire universe is made up of the one particle. It can't be. It has to be magic, because the particle has to organize itself. How can you do that? It's got to have a brain, and it's got to have parts. And that's where you get into Borchert's thing. You can't have one particle all of a sudden make the entire universe, but you can have one particle act and make different parts of the universe, and the G1 particle at our level does that. It moves in different directions. And you say to me and my father, well, how can one particle be that way, and why? So why does it become, why does it make gravity? Why does it make, very good.
We tend to ignore the nucleon N1 particle. We tend to ignore that one.
Yeah, but that's okay. Let's keep it at this. Right now we're trying to talk to them about the universe, and if we have like one particle, and it's just its movements. The question will be, hey, Dad, I will ask you, why do we have those flows? You give me these 4 flows. Yeah. It's magic. They just all of a sudden decide, these G1 particles says, hey, let's go around in a circle. So why do they?
Like old westerns.
Right, but why? If someone asks you why do particles organize themselves, why?
They don't. Something outside organizes them.
Oh, very good answer. And so when you were working with the G1 particle and the gravity, again, we're going to get through, people who want to know, this is Farouk's question. Bob, have you finished your new book on electronic circuits yet? The answer
Yes.
is no.
I have it.
No.
I have a first copy.
No. Dad, we made a copy, which is a preliminary copy to see about how it's about 50% done. Okay? So we just printed it out. That's the problem with today. So you can make your book, print it out, send it home. It looks like it's done. No, we have a lot to work on it yet. So we have a preliminary version, but we really need to work on it, Dad and I, on that. Okay? So answer is no, but it's coming. So back to the question. When did you look at the advertising, when you were looking at gravity, and we call the graviton, and which we now call the G1 particle, when did you realize there had to be some outside force to do something with that? Or not even when, but where were you that you came to that conclusion?
The fact that there's an outside force, which is the G2 gravity, I realized that when I compared G1 gravity around the Earth and the refraction around a prism.
Okay. And one of the things is light travels at the speed of light. And people always are really looking for, is there something in the universe that travels faster than the speed of light? What's the answer?
If you're going to bend light, especially to make a rainbow, it would be really difficult to do that with some force that only moved at the speed of light. You might bend the light, you might speed it up somehow. No, you wouldn't even do that.
You can't, because if it's going at the speed of light and you have... So the idea is you've got this thing going at the speed of light like this. Okay? Here's the speed of light, right? Like this. If you have to try to make it go faster than the speed of light, and all you have is other particles that go to the speed of light, it's not going to happen. So what's the conclusion? What do you have to say?
Well, if you're going to, like I said, if you're going to have refraction and create a rainbow, or dispersion, not just refraction, dispersion.
So if you take light and move it, right? That's what it's doing.
You got to move the light, and you got to move it in a controlled way. What I find really interesting is if you, and I'm going to try to paint a picture. You've got white light coming in and into a prism, triangular prism, and it spreads out into a rainbow. Okay.
Or just a rainbow when you look out in the sky, right? That's a rainbow, same thing.
But you can get the same effect with billiard balls, if you will, of a different weight, lead, wood, and cotton, and you give them the same force, you can get the same effect of like a rainbow effect, only mechanically. I've drawn a picture like that.
Yeah, so in other words, for light to move, so for light to change direction, so you put a stick in the water, right? And the stick looks like it bends, right?
Yeah.
Well, the stick isn't bending. If you're a little kid, you may think that, but the stick's not bending. We know everyone gets this idea that water changes the direction of light, correct?
Yes.
And so for something G1 particle going the speed of light to change direction, you need a force that's going faster than light. And that's where you get into the levels of the universe, meaning there are particles, G1 particles, and then there are really small, faster particles at another level. And that's what we call G2 level. And there's a G3, there's a G4, there's just levels of the universe. And that's what makes particles move the way they do. You don't have light changing into rainbows, meaning light's going like this and it gets changed, its direction gets changed. The only way you can change the direction of lights of particles, what people would call photons, or what we call waves of particles, G1 particles, how we change the direction is to have a force field that is faster than light. And so that field is a gravitic field. That means you have teeny
Version of that.
teeny particles moving around in random directions, really small, really all over the universe. And those G2 particles will make the G1 particles. Think of the G1 particle now as a planet or a moon or a sun, and that the gravity that we have, the G1 gravity for our sun and moon and all those things, and the Earth, and the planets, we have it down a level so that the particle that we call the G1 particle, coming in waves like light comes in waves, will be diverted by a gravitational field, but it's a smaller one. It's down much smaller. So the answer to the question, is there faster than light things in the universe? Absolutely. If you get down a level, you got faster than light. Way faster than light. And then if you go down below that, you're going to get faster than that. So the idea...
If you say down a level, are you talking, you're talking about a subatomic atom?
Yeah, levels of the universe you have, like, we do have that. In our book, we do have a levels of the universe kind of thing that people can see. And let's see, do we have those? Of course we do.
In fact, it's the only source for a particle faster than light is a subatomic atom.
Right. So what we have here are particles. We have particles that are much bigger of things, and we have particles of galaxies, particles of stars, particles of atoms. We have particles of G1s and N1s, and particles of G2s and N2s, all the way down. So, and all the way up. So that's the kind of idea. So it's really kind of exciting because, think of it, if we know that the force, and if the G2 force, Dave, what is that? It's magnetic force. Did you notice how magnets, especially strong magnets, or all magnets, they defy the force of gravity? If I have a magnet here and this magnet, and they attract, and this magnet won't fall down. Gravity will not push that down. That magnetism, the force of magnetism, is greater than gravity. Why? It's because magnetism is mostly from the G2 force, and G2 force is faster than light, much faster, and so it's got a greater force. And that's why we call it the strong force, and it keeps the electron going around the nucleus of an atom. So that those are very strong force. So magnetic force is the result of the G2 gravity. The electron going around is also G2 gravity. Again, just go down. Remember how you always thought the atomic model, and they say Bohr's atom and the atomic model doesn't work? Well, no, it's not a simple problem like that. It's not one thing going, or not one nucleus with one thing going around it. In our model, we think it's more than one particle for hydrogen. It's quantum particles, just like light is quantas, or quanta is a quantity of particles that move together in waves. So all of these things give us the idea that you can move faster than that there are things that move faster than the speed of light. Now, can we get spaceships to go that faster than the speed of light? We have a model for it. People can use it to try to get that answer, but we don't know. But I was thinking, if we have G2 fields, like it's the strong force, and the thing that makes magnets go together with such force, is we could make a G2 transmitter with G2 particle waves, and those things would go probably to Mars in a fraction of a second.
You want to emit the G2 out of the back end of a rocket light type.
Well, no, I'm not talking about rockets. I'm talking about communication. Oh. That if you were to make an electronic circuit that dealt with G2 waves instead of G1 waves, you could transmit at superluminal speeds.
Yeah, but the question is, what do you make that out of?
The question is to let other people do it, because we just came up with the model, so we can't do everything. So, anyways, again, if you want to purchase our book, you can go to Amazon right now and buy it. And we have also an e-version, ebook of the book, which is $3, $2.99. So you can read it on your phone and stuff, and it looks pretty good. I made sure that if you have a smartphone and you buy the ebook, you can actually get real close to the graphics, because our graphics have all these little particles, and you can zoom in, and it's very refined and fine. So it's pretty cool. So again, the idea of these talks is to talk about the universe, the particle model, but how people could do things and how people could use this model in the future. So I'm going to kind of cut it off now. We've gone about 40 minutes, but our goal is to do this once a week, if not more. And I think the next time we want to talk is what are the things that people can apply this to that will be useful and be able to answer questions. And some of them will be like the electric universe. I think that would be an interesting one, is the electric universe has electric fields saying it causes gravity, that there are Birkeland currents that are currents that go through the universe, and things are linked to that. And our model can explain a lot of that stuff. Some
I
of
haven't
it
looked into that at all.
Yeah. And the other thing we want to talk about would be electronic circuits, right?
Yeah, this is what he's asking about, and
right, but
it's
that's
really exciting how the particle model explains the transistor and the diode. It's amazing. I get excited. I don't get excited very often, but I get excited about that. And Farouk, you'll really love it when we get to that point.
Yeah, I mean, so we've got this book, and we've printed it out, but we really need to go through it a lot to get it kind of organized, to get its diagrams, because it's kind of put together from the other book and then added to my father has. So we really want to work on that. And so that'll be our next time. We're going to talk about how the particle model can be applied and who would use it in the future. And those kinds of things, and kind of exciting things. So thanks so much, guys. Again, we don't want to keep this long, because we can talk about obviously the particle model all day long. But again, these are like talks about if the particle model's really accepted. We're going to talk about it, what it is, and how into the future, that if it were accepted, what it all means and stuff. So today, the summary is that our model isn't a model of equations. It just simply says that what we call gravity and light and magnetism and electricity are simply the way particles move. So you don't have you don't have gravitons, you don't have magnetons, electrons, and you don't have light. Those things are simply what we have classified as movements. That's why we people say light's a wave and it's a particle. It is. It's a wave of particles, actually. And so again, this idea that there's one particle with a name, and that was the downfall really of Newton, right? And everybody else. They were trying to make one particle have frequency, which is really, really weird. Think about it, folks. Frequency means frequent. If something is frequent, what does it mean? You have to have more than one. If you have one bus come by your house and people ask, what's the frequency? You say, I have no idea, because only one's come by. If you have to have frequency, you have to have more than one. So it's kind of weird that people conceptually were trying to make a particle, like Newton was trying, to make a particle have frequency.
The photon, yeah, that destroys the photon.
And it's funny, that's why people insist that it's the wave, right? And that's why so many people are etherists, because an ether, light requires more than one particle, right?
Yeah, drawing a wave inside a particle doesn't get it.
Yeah, it doesn't work.
That's
So
that's the way you see photons depicted, with a particle with a wave inside. That's impossible.
right. So anyway, so that's the idea. The particle model says that at our level of the universe and all levels of the universe, you have random directions, you have circles or orbits, you have particles flow all together in one direction, or you have waves of particles coming at you like this. Waves, not, yeah, it can be one particle, but in our opinion, it's usually waves of particles. So that's it in a nutshell. The entire universe, up and down, from the infinitely up and infinitely down, it can be described in these four movements. And that's a theory, I guess. It's a model.
A model, yeah.
I guess. So, okay, thanks so much, everybody, and thanks for coming by. Thank you, Farouk. Thank you for Muhammad, and thank you, all you people. Remember, if you do see us live, and even if you're not into it, give us a thumbs up. Support your geeky friends who think they've solved the whole universe, mad scientists, and of course we think of ourselves as geniuses, and all of everybody else stupid.
Without the hair.
No, it's not. Yeah, we can't keep up the Einstein idea of the mad scientists, because we need to make our hair go funny and not care about it. But thank you all, and we'll be on now and then. Stick around, see it. I hope those people watching the
Nice to see you. Well, all of you.
all of you. Yep. So let's go out. Let's put up some videos. So here we go. So, of course, my dad really likes the logo I came up with, our model, right?
Oh, yeah.
And wouldn't that be weird? Wouldn't you think it's like Newton has Principia Mathematica on his book from 1670, whatever? It's kind of 78, I don't remember. It would have a logo.
1660s.
He should have had the Apple logo, but then of course Apple computers have a bite out of that. And so our apple within an apple just says there's gravitational fields at different levels, and that's what that kind of comes from. And Dad really likes this, and I think this is his favorite logo here.
Yes.
So we're going to run it. So in the future, maybe they'll have like the golden apple, and within an apple award for, instead of the Nobel Prize, which gives it to people doing work that's not good at all.
The
that will be
Apple Award, huh?
Yeah, I would imagine. I'm just thinking what kind of percentage of the Nobel Prizes that were given out were going to be like thrown away, because they're just about stuff that don't, like, neutrino, gravity waves, those kinds of things. So, yeah, we'll have to talk about gravity waves. All right, we're out, folks. Say goodbye, Dad.
Bye.
Dad.
Dad.